Hi, my name is Emmanuel, and I'm going to present an investigation of damping effects among a couple of phonon crystals and metamaterials. Periodic structures are made of a number of identical unit cells or substructures that create a continuous structure. In letter A, we have a periodic structure composed of geometrical pattern, whereas in B, we have a material periodicity in the periodic structure. The green color could be steel, whereas the gray color could be aluminum. So this geometrical or material periodicity can induce a phenomenon called band gap, where the elastic waves are forbidden to propagate, which means that the vibration amplitude inside the band gap region decreases. Most of the investigations presented in the literature regarding periodic structures basically ignores energy dissipation during equations. So the paper herein will investigate the effect of adding damping in periodic structures. Here we're going to study for different configurations of periodic structures. System A and B are phonon crystals, whereas C and D are metamaterials. Both A and B are diatomic periodic structures. The difference that in system B we have mass M1 and M2 attached to the ground. In system C we have a monoatomic metamaterial. There is a vibration observer represented by mass Mr. D is kind of like the same as system C, but it is a diatomic periodic structure. On the left side, you see all the periodic structure, and on the right side, you see the unit cell of each structure, which represents the smallest element that creates the pattern in the structure. So in order to study the band gaps in each structure, we're going to use the transfer matrix method that is used for drawing the dispersion diagrams. From all the dispersion diagrams, we can extract the band gaps. So here's how the transfer matrix method works. We're going to use the system A as an example. Here in the right side of the figure, we have the unit cell of this periodic structure. So with that, we derive the equations of motion for the unit cell, and we place those in matrix form. So here you see the mass matrix M, damping matrix C, and stiffness matrix K. So then we generalize the equations of motion and place them in the frequency domain. The term inside the parentheses is the dynamic stiffness matrix, which we're going to partition it in the left and right boundaries of the unit cell. We then relate the motion of the left side and the right side with a matrix T, and after some mathematical manipulation, we arrive at an expression of T, which is nothing more than the transfer matrix. So using Foucault-Bloch theorem, we can solve the eigenvalue problem and obtain the eigenvalue lambda, which has a propagation constant mu, which has a real and imaginary part. The alpha is the attenuation factor, and beta is the phase constant. So when alpha is 0, we have a passband, and where we have a alpha different from 0, we have a band gap. For the numerical results, we're going to apply a harmonic excitation force with frequency ranging from 0.1 to 150 Hz. We're going to apply this force on one end of the periodic structure. With this, we're going to obtain the attenuation factor, the frequency response function, and also the spatial attenuation of each system for different levels of damping ratios. So in the table below, we have some parameters. So mass M1, M2, and MR, we're going to use 1 kilogram, 10, and 10 kilograms. All the stiffness will be 100,000 newton per meter. And for the damping ratio zeta, we're going to use 4 discrete values. Here we have plotted the attenuation factor and phase constant diagrams for the 4 different periodic structures. In system A, we can see two well-defined bandgap regions, one starting from 20 to 75 Hz and the second bandgap region starting from 77 to 150 Hz. As you increase the damping ratio, you see that nothing happens inside the band gap regions. The attenuation factor value is still the same. But in the pass band, especially higher frequencies, you can see that the attenuation factor becomes different from zero. So here you can see a band gap merging phenomenon. As you keep increasing the damping ratio, the first and second band gap regions they will merge. System B, you can see three well-defined band gap regions. And the same goes here. As you keep increasing the damping ratio, you see nothing happening in the band gap regions. The attenuation factor value is the same. But in the pass bands, especially at higher frequencies, you can see here the second and third band gap region merging as you keep increasing the damping ratio. For system C, you can see a band gap due to the vibration observer starting from 15 hertz going to 50 hertz. And as you increase the damping ratio here, you see that the attenuation factor in fact decreases. So if you wanted to increase or reduce your vibration amplitude in your structure, it's not a good idea to add a damping on your vibration observer. System D, you see three band gaps regions, the first one due to the vibration absorber, and the second and third due to the masses M1 and M2 being different. So as you increase the damping ratio in the vibration absorber here, in the band gap, you see that the attenuation factor decreases, just like in system C. And here, between the second and third band gap, you see the merging phenomena due to the band gap. So here we have plotted the frequency response function. And system A, for instance, you see that the two band gap regions here between 2075 Hz and between 77 to 150 Hz. As you increase damping, you see that nothing happens with the admittance values here inside the band gap zones. But outside in the passband regions, you see that the vibration amplitude decreases, as we would expect from classical vibration textbooks. Same goes for system B here. Inside the band gap, you see that nothing happens when you increase the damping. The admittance values is pretty much the same. But in the passband regions, you see that the resonant peaks decreasing their values. For system C, you see that the admittance value here that increases when you add damping. So as we have said before, it's not a good idea to add damping in your vibration absorber, as you're going to increase the amplitude of vibration. Same is true for system D. Here we have the spatial attenuation for each different configuration. So for system A, we have applied 72 Hz of harmonic excitation force, and for the other configurations, 88 Hz. So we have no damping here, and you can see all the masses moving as we would expect in the passband region. You won't expect vibration amplitude decrease. Now, when you add damping, you can see that the masses at the end of your structure, they barely move. And this is what we would expect as we put damping in the system. We are removing vibrational energy from all the system. So it's a good idea to add damping in your system when you have a lot of pass bands in your structure, as you're gonna decrease the vibrational amplitude, as you can see in all the four figures here. Now I'm applying excitation force of 30 Hz, which corresponds to a band gap region for all the structures. As we can see, it makes no difference when we add damping. The response of the structure is going to be the same. We can see that the mass barely moves as you go to the other end of your structure. So here, it doesn't matter if you add damping or not. In the band gap region, the response is going to be the same. So for the conclusions, we had studied the damping effects of periodic structures. We saw a band gap merging phenomena as we increased the damping ratio in those passband regions. We could also see that the attenuation factor value around the local resonance decreased in metamaterial when damping is added, and also that little effect in spatial attenuation is observed in frequencies where a band gap exists. Thanks everyone for your attention.